What's up? What's up? It's your man, Jimmy Chan. All right, so we are talking about probability rules, and here are some definitions that I'm going to let you read on your own through the PDF. All right, so the important ones that I want to kind of bring out is sample space, right? Sample space as of a probability experiment is the collection of all possible outcomes. An event is any collection of outcomes from a probability experiment, and event may consist of one outcome or more than one outcome. All right. So here, a probability experiment consists of rolling a single fair die. So the word die is the single for dice. Dice is actually plural. Okay. Identify the outcomes. Well, just so you guys know, outcomes all the possible outcomes are going to be, if I roll a die, is I'm either going to get a 1, or I'm going to get a 2, or I'm going to get a 3, or I'm going to get a 4, oopsies, or I'm going to get a 5, or I'm going to get a 6, right? So those are all the possible outcomes. And now it says determine the sample space. Well, the sample space is all the collections, right? So for B, my sample space S is equal to 1 or 2 or 3 or 4 or 5 or 6. Excuse me. So the rules of probabilities. The probability of any event E must be between 0 and 1, and the sum of all probability outcomes must equal to 1. Okay? So if we look back at the die, what we saw is, so we take the die example. Right? So the probability of rolling a 1 is 1 out of 6. The probability of rolling a 2 is 1 out of 6. The probability of rolling a 3 is 1 out of 6. The probability of rolling a 4 is 1 out of 6. Probability of rolling a 5 is 1 out of 6. And the probability of rolling a 6 is also 1 out of 6. So based on rule number 1, it says each probability has to be between 0 and 1. So as you notice, yes, every one is 1/6, which is between 0 and 1. For the second rule here, the sum of the probability must equal to 1. So 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 must equal to 1. Can't be less than, can't be more than, it has to be exactly 1. And if I add all 6 of these 1/6s together, I will get a sum of 1. So therefore, I'm good there. Okay, doke. All right. Let's continue on. So empirical approach versus the classical method. So let's instead of trying to explain it to you, because if you were to look at the definition, or I should say the formula, what you will see is that they're pretty much the same. And you're like, okay, so what's the difference? You just reworded it differently. Well, let's use the example and kind of go through both ways. And this way you can see what's the difference between the empirical versus the classical. All right. So suppose that a survey asked 500 families with 3 children to disclose the gender of their children, and found that 180 of the families had 2 boys and 1 girl. So the first one wants me, I should say, part A wants me to find this probability using the empirical. So part A, empirical. Okay, so with empirical, it wants me to find the probability of 2 boys and 1 girl. Well, that's gonna be, well, how many families were asked? You're gonna say 500. Great. How many families had 2 boys and 1 girl? You're gonna say 180. So I divide those two. I'm gonna get 0.36. Right. So if that's the case, then this is my so-called, and it's between 0 and 1. Okay. So this would be my empirical way of finding the probability. Now, for the classical, okay, what I would do is assume that there is equal outcomes for either boys or girls. So if someone gave birth to the first child, it can either be a boy or girl. And if they gave birth to a second child, it can either be a boy or girl. If the first child was a girl, the second child would either be a boy or a girl. And then let's say they had a third child. If the first two was a boy, the third child could either be a boy or a girl. If they had a boy and a girl, the third child could be a boy or a girl. If they had a girl first and a boy second, the third child could be a boy or a girl. And if they had the first two as girls, the third could be a boy or a girl, right? So we have boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and then girl, girl, girl. Okay? So we look at it, how many of these have 2 boys and 1 girl? 2 boys, 1 girl, 2 boys, 1 girl, 2 boys, 1 girl, and that's about it. How many possible outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8. So 8 possible outcomes. So with the classical method, there's a possibility of 3 of getting boys, 2 boys and 1 girl out of 8 possible outcomes. And that's going to give me a probability of 0.375. Okay. So notice that these are going to be different. All right. And it could be different because that the empirical doesn't have enough trials yet, right? Maybe you needed to ask 5,000 families or 5 million families to figure out that it might get closer to this, given the fact that this is, assuming everything's even, right? But again, this is not always necessarily true either, right? Sometimes, your family has a twin gene, your chances are you're going to have twins, right? And if you have the, boys genes, then you might have more boys than you have girls. So that all kind of gets played into this whole thing. So sometimes it's definitely hard to try to figure that out. I hope this helps. Any questions, please let me know. See ya. Bye.